Hi, I'm Steve Sands, Technical Consultant here at Festo. The perception of smart maintenance is it requires a sizable investment in both time and money. Together with RS, what I would like to do during the course of this video is show you an alternative approach with a very easy first step for a proof of concept of smart maintenance. Whenever a mechanical asset is running, at some point there will be wear and tear and degradation. After that, there may well be a breakdown incident. When that happens, then you're trying to do maintenance out of sequence. You haven't prepared for it, you may not have the right people or the right spares, parts in place ready to replace, which gives you additional breakdown time. During the time period leading up to that, you may have inconsistent production, you may have damaged quality, you may have increased energy, and you will not be getting the performance out of the machine that you expected. It's going to be better for us if we can pick up on this wear and tear and degradation at an earlier point. And this is where smart maintenance comes into play. We're starting to use data to predict failure, and we can observe this, or our machine learning algorithms can predict this far earlier than we can observe it by physical things that we can see and hear. So the acquisition of data is going to rely on sensors, and these can be anything from fairly binary, simple cylinder switches, little devices like this, can become slightly more sophisticated if we want to use things like I/O link device sensors, which can give us a lot more data, a lot more information, and easier to parameterize at a distance. Also, smart devices with communications with microcontrollers also have great access for data. So all of these can provide us sensor information into our data stream. If we now start to have a look at the graphic behind us, we're gathering the sensors, which gives us our raw data. We need to collect that data into a usable format, we need to communicate it, and we need to make it a logical aggregation of data. The problem with data is it's often inconsistent. You'll often have duplications, inconsistencies, missing pieces of information, and it all needs to be cleansed. Even a simple thing like a flow sensor, it may be measuring in different units over different time bases. If we're only looking at a number in a database, it doesn't give us a basis for comparison. So we need to be able to condition the data before we can actually use it. We then move out of the operational environment and into the IT environment. And this is where we actually compute and process the data and then turn it into valuable insights that we can actually use. Only once we've identified the key data that we need and we've cleaned the data itself up, then the project team can then start to select the algorithms they need, train the algorithms and optimize them to give the output they need. So this can really vary in complexity, and that's where the time can come in as well. So this is where the art of the data scientist comes in, and they need to work in refining the selection of the algorithms. It takes time, and typically I would say 2 to 3 months would be normal in a project like this. But if there's a lot of assets, they're very different, and even they're not reoccurring, then it can take longer. Project costs can be anywhere, I would say between 15,000 and 25,000 would be quite normal. It's not to say there's not a good payback on return on investment, but any project like this will require stage gates. It requires proof, evidence before you're going to progress over such a long project with so many people committed. So it's a sizable investment that you're going to make. What I want to show you in a few minutes' time is a different approach where we can just use a plug and work application where we can get it running literally in minutes. Let's have a look at these plug and work solutions and see what they really mean. It means about being able to apply this technology without the data specialists, data scientists, data engineers. It means we can implement it in hours or minutes even, not in months. And what we're doing is we're installing a function block within the PLC on the control of the machine. And within that function block, there's a Docker container. And that has got everything that we need to be able to implement these algorithms. So in other words, what we can do is install the function block just as any programmer would do within the PLC environment. In the example I'm going to show you in a minute, we're using a Siemens controller, but we have an Allen Bradley controller on the back wall here. Either system we can work with equally well. Within that Docker container, we have the AI algorithm, but we also have a visualization dashboard, and we have the method of communicating out if we find an anomaly. In other words, we can describe the anomaly through an MQTT type telephone type messaging system, or we can put it out through an OPC UA system into an open environment there as well. So for this example, we've got a rig here which has just got a small pneumatic cylinder on there. We've got the ability to cycle it backwards and forwards, and we can also introduce some faults. So in other words, I can increase the friction on the cylinder, putting my hand against it, or I can induce leakage on there. And normally, we'll be able to show this in a minute, we'll have a health score for the actuator. When it's green, it means it's healthy. If there's an amber, there's something to be interested in, to look into. And when it's red, obviously this is a warning that something needs to be actioned. And this very simple output enables a simple trigger then for maintenance to work with. Let's have a closer look at the rig and we can look at it cycling. So within our small demonstration rig here, we've got a small Siemens S7200 PLC underneath here, where the programmer will have installed the function block just as they would have done any other function block within their normal PLC programming. They don't even need to activate it. They can embed it at the time of programming it, and then later on the end user can activate it when they want to, if they want to. Also on the rig, we have a standard pneumatic cylinder with a sensor at both ends of stroke. Underneath there is a small valve that is cycling the cylinder. And as the cylinder goes backwards and forwards, we can measure the time base between the trigger signal to the valve to send the cylinder out, when the cylinder starts to go out, and when it reaches the end of stroke. So we've got quite a lot of data there that we're gathering from a very simple sensor, just a simple binary on-off sensor. If I just cycle it for a little bit, I won't try and talk over it all the way through, but here you can start to see the dashboard that's embedded within the function block starts to build. So the data on here will start to build up, and with every cycle of every stroke, the system is learning a normal condition. So once it establishes a norm, we can then start to put an error in if we want to. I can restrict the stroke of the cylinder with an extra force, and then we'll see the health score immediately start to drop. So on the screen there, you'll see the green indicator start to drop down. If the fault continued for longer, it would go to amber, it would go to red, saying that we do have a fault occurring. Same thing if a leak occurs, so it's a different fault, but we also get a health score that's coming through that. What you don't know from the system like this at the moment is what the actual cause is, but at least you have an indication there is a problem and where the problem is. It can be implemented very easily in different environments. We can put it into the premise, edge, cloud environments, and it can even run on an IPC, on an industrial PC, if you don't want to use a PLC environment. Of course, what we do need to then do is to track the overall results. Look at how many failures we detect in advance, what breakdowns we prevented, and what the cost saving there is to the organisation. Then we've really got a strong business case to build up investment in the future for larger and repeated projects. So there are 5 key steps that we can take here in this plug and work approach. The first one is to identify a critical component where we can monitor it and where the cost of failure is relatively high. That way we can get a fast return on investment. It could be that the product itself is expensive to replace, or it could be the cost of wastage while the machine is down is very high. Either would give us a good justification for further investment. I would recommend we use sensors that are already in place. We don't need to go looking for additional inputs. Let's see what we can already use on machine, on device. Once we identify these 2 criteria, the important thing then is we quantify the value, and this is gathering those metrics. Once we've got it, we can scale up. We can use the success for further investments, and of course we can share the success through the organisation as well. Thank you for watching this video. I hope it's proven valuable for you. If you'd like to know more about different maintenance regimes, please follow the link that you can see on the screen. And don't forget to like and subscribe for more practical engineering guides.